Okay, I will start on the matter of time. Welcome everybody. It's great to see you guys. It would have been great to be in Boston. The weather is perfect, the colors standing, and if we are lucky next year, we will be recording Boston. Please, guys, close the microphones. We have right now 44 panelists, and right now we have 117 attendees, but the number keep growing like crazy. So yeah, 530 attendee register, and I have 60 panelists. So hopefully we will not crash the web. And so few things before we start. I share in the chat with everybody, and I can share it again, an important link. That is the link of our Q&A in the FNIRS webpage. When you go to the webpage, let me share the screen 1 second. I don't know what's in my screen, but so you end up in this page. And if you want to go the first session, hardware development, you click on the link and you see at every talk, there is this little green mark and you can ask questions. We ask a few random questions right now to make sure everything works. We don't know if it works really well, but we are trying. The thing is to answer question and to participate to the commenting and the liking, you have to log in and press account. And if you're a FNIRS member, paying member, you should have your password and such. If you are not, what's happened? Why? Okay, sorry, I stopped sharing my screen. If you are not a paying member, you can log in for free. You will receive an email, so it takes few minutes. Do it ahead. And we can also look at the chat here and the Q&A here. I have several co-hosts. I don't, in particular, the moderator of the first session are Adam Liebert and Rickson Mesquita. The moderator of the second session are Lauren Emberson and Stephen Perry. They will go through the question. And so they will look at the chat, at the Q&A, and the web page. And the speaker will be able to answer the question after all the 7 talks, and they can ask live. We will love, so there is an attendee that raised their hand, but it's too confusing for me. So I have 7 co-hosts, they can help. But so what I wanted to say, welcome everybody, and I want to pass the word to our president, Claire Elwell. Claire.
Hi, so I just wanted to welcome everyone as well, and the response to this initiative has been overwhelming. I want to thank Mari for coming up with the idea, and David also. I think it's a really great way of keeping us connected. I think we're going to be excited at the volume of data that we're going to be able to share, and I'm really hopeful that we're going to have lots of discussions around that too. Just while I have the opportunity to speak with you all, just a few other things to remind you that we have in progress to keep the community connected. We have a series of research webinars which are being organised by Felix Schokman, a series of educational tutorials being organised by Judith Gervain. We have a new committee that's being formed for equality, diversity and inclusivity, which is being chaired by Joy Hirsch. And we are actively trying to increase the breadth of our communications. So those are things that we're trying to do while we can't meet in person to keep everyone connected. But please do feel free to contact any of us, myself, Mari, Martin, David, with any ideas that you have for what we might be able to do to serve the community during this time. But, thanks again, Mari, for putting this together.
Thank you, Claire. So on the matter of time, I pass the word to Rickson and Adams, the 2 moderators of the first sessions.
Hello, so good morning, everyone. Let's start the first session of this Data Blitz. I'll be moderating the session with Adam Liebert, who is also here. So the first talk is going to be by Professor David Boas, and the title of the talk is Neuroimaging in the Everyday World. You have 5 minutes, David.
This is actually very important. We cut the presentation around 5.5 minutes or so. So we will stop your screen sharings. We collect the time. Thank you, everybody. David, you're muted.
Please unmute yourself, David.
How do you like that? You can see my screen but can't hear me. So I'm happy to give you updates from the Neurophotonics Center, where we're quite excited to really begin a new major effort for ourselves, which is neuroimaging in the everyday world. I think this is a direction that many in the field are already headed in. So to start, we really kind of got started in this only about 3 years ago. I had a gap in FNIRS funding for a few months. And so in a way, you could say I started off my current FNIRS research only 3 years ago when we got this small grant to establish an FNIRS ecosystem for open software and hardware dissemination. So I'd like to give you some updates about that. We were able to use that funding to finally push through this shared near-infrared format that many of us in the community had contributed to over the last 5-6 years. Finally, with great help from Qinshin Feng, J-Dub, and Ted Huppert, and others, we've released that on GitHub. Many companies are now adopting this for facilitating the sharing of near-infrared format data. We also are encouraging the sharing of data, and we've created a metadatabase at openfnirs.org, which is really just serving as a searchable clearinghouse database, so you can find openly shared data out there on the web that may be shared on any number of websites. In addition, we've used this small grant to further advance Homer and Atlas Viewer. We now have a third version of Homer that's been released. This supports SNRF, session and group level processing. You can find it all on GitHub. We have a very active Google group. We have lots of training materials and past workshops at openfnirs.org. And really, I need to acknowledge Jay Dub, who's been really pioneering this work for the last 10 years, and Stephen Tucker recently has been a great help to him. So we could not have gotten this grant just with software. We had to talk about hardware as well. So we've been developing our own wearable FNIRS system. So this is the prototype that's our current prototype. We're looking for beta testers to help us test this system. We are funded to give away about a dozen different systems for free. Along the way, we have to build a GUI for this. Antonio Ortega has been developing this GUI, and he's been developing it in a way so it'd be very easy for others to adopt it as well for their own systems. And we've been designing these caps. You can use Atlas Viewer actually to design your own caps and then have it 3D printed. So really, over the last few years, 4 years, there's been an explosion in wearable FNIRS systems. So there's several companies that now have wearable FNIRS systems available. I apologize to any companies that I've missed. This is advancing very rapidly, and Rob will tell us in the next talk about some of his advances. And we're clearly going to see a lot of integration with EEG, eye tracking, and more. There's many academic systems. As I said, Rob is speaking next. And on Wednesday, Qinshin Feng and Joe Culver will be talking about wearable systems as well. So there's clearly an explosion of activity here. This is the next step for the FNIRS field. And we believe that everyone's going in this direction of neuroimaging in the everyday world. And so we were very fortunate just to be awarded last month a large Brain Initiative grant from the NIH to help us work with everyone else in realizing this amazing vision, I believe, of neuroimaging in the everyday world, where we're going to combine FNIRS with EEG and eye tracking so that we can capture how the human brain is working, not in the isolated setting of a laboratory, but out there socially interacting in the everyday world. So there are three aims. There's the hardware, which I think, as being led by the commercial companies, this is a realizable goal. The real challenge is then, kind of the unknown solutions will be in the experimental design and analysis. How do you actually do brain science experiments of subjects engaging in everyday activities? So this is a new frontier that we're all going to have to work together on to solve. So I want to wrap up by acknowledging it's been a great pleasure working with Alexander von Lumen the last 2 years when he was a postdoctoral fellow in my group. He really helped drive this vision and helped us get this grant award. He and Miriam, it was really fantastic watching Alex and Miriam work together the last 2 years together. Miriam Musil has been working with all the cognitive scientists at Boston University who are itching to implement this technology for their studies. Bernard Zimmerman is the electrical engineer putting the hardware together, working closely together with the PhD students, Antonio and Joe. Very lucky to have Anderson Chen coordinating all of these efforts. Really need a project coordinator there. And Priya Farzam is going to be working closely with Miriam on the applications, and happy to have our newest postdoc, Yuan Yuan, join us. So I'm done. Thank you for your attention.
Thanks, David. So just remind everyone that all the questions will be at the end. Okay, so for now, we're going ahead with the second talk, which will be delivered by Rob Cooper. And the title is The Promise and Practicalities of Wearable High-Density DOT in Newborns, Infants, and Adults. Rob?
It's asking me for a password to share. Oh, hang on. I'm sorry. What's happening? Where's it gone?
We can see your slides.
You can see my, okay, you can see my main slide. Great. I'm sorry. For some reason it asked me for a password. Okay, I'm sorry. I'll get going. Thank you. My name is Rob Cooper. I run the DOT Hub research group at University College London. Thank you for having me speak today. I'm going to be talking about a range of work that's been going on in my group and UCL more widely for the last few years. So first, I want to acknowledge all the lovely people I work with. So it's a mixture of PhDs and postdocs, but also a team from Cambridge where we have a collaboration called NeoLab, which is focused on the neonatal brain. So the basic premise that my group has been working from for a few years now is that we know that high density DOT is superior to FNIRS, but why is no one really doing it? And the reason that no one's really doing it, we think, is that the systems that exist to allow this are large and cumbersome and expensive. So we've been working for a number of years on moving the electronics to the head and developing these wearable, not just wearable FNIRS systems, but wearable high density DOT systems. So we work closely with GAL Labs Limited, which is a UCL spin-out company, which David mentioned, and now has these modular wearable devices that put all the electronics on the head and remove the need for optical fibers. And in my group, we're also working on advances on this kind of platform to miniaturize these things yet further, and particularly to make them appropriate for neonatal subjects, or at least more appropriate for neonatal subjects. So one of the things we've been focused on a lot in the last year is demonstrating these technologies for the first time at different stages of prototyping. So we undertook a study with 6-month-old infants. So this infant is wearing 12 of these modules, which is equivalent to 84 optical fibers. So we ran a study with 20 of these infants from 4 to 7 months old using a very well-established visual social stimulus. We were able to get greater than 40 millimeter separations in every single baby that we studied. And the general acceptance of this technology seemed very good in this population. So we're able to get these lovely canonical HRF response maps. And as you can see, we have these high density arrangement of channels. Because of the density, we also have a range of source detector separations. So from the left to the right here, I'm showing the hemodynamic response to one of these social stimuli from 10 millimeter separation all the way up to 45 millimeter separation. As you can see, that HRF is growing in amplitude with source detector separation, which is a very good indication that this signal is in fact coming from the brain. We can also obtain three-dimensional images from our data sets with these high density arrays. So in the middle here, you can see the oxy and deoxyhemoglobin group level maps, which show these fairly broad responses. It's a fairly big stimulus, but these are localized in all 3 dimensions. Because we have these high density arrangements of channels, we can subsample our array to produce something that's a bit more like a traditional FNIRS array and actually directly compare, explicitly compare the kind of benefits we're getting from these devices. As you'd imagine, the images are much better, but perhaps the biggest take home we found is that the actual SNR is noticeably better as well. So the high density systems are producing something like twice the SNR of a low density equivalent, which arguably means you could get the same data with a quarter the number of babies. We can also look at consistency of those responses. So this is a heat map showing the number of subjects that responded in a given location. So the high density at the top and the low density at the bottom. All 17 of our subjects showed a response in the superior temporal gyrus to this stimulus in our infant population. We've also been benchmarking these technologies in the adult using kind of classic visual stimuli paradigms. Again, we kind of get similar results in the adult population. So we get very nice HRFs, localized responses. And again, we can produce these heat maps that demonstrate the consistency of that response and actually directly compare it to a kind of FNIRS style density equivalent, which not only produces a more diffuse, lower SNR response, it's actually, in this case, at least it's dislocated. Again, because of the high density, we're able to reproduce some of the kind of seminal images and movies that Joe Culver's lab have been producing over the last 10 years or so, but now in an entirely wearable device, which we're really pleased with. There's a lot more going on. I don't have time to talk about. We're expanding the number of tiles we're using. We're already doing 24 tiles, which is equivalent to 180 or so fibers. We have neonatal applications. As David mentioned, we're also interested in eye tracking and EEG symbiosis with these devices, atlases, and we're also interested in studying babies while they're laughing, which we think would be an interesting challenge because there's a lot of movement involved, but it's the kind of thing you can only do with these types of technologies. So that's my 5 minutes. I did promise Gemma, who wasn't able to speak today, that I'd mention her new lab. So she's just won a place at Cambridge to start her own group, and she has 2 PhD positions available at her new neurooptics lab. So do get in contact with Gemma if you're looking for a PhD.
Okay, thanks, Harab. So let's go ahead. Our third talk is going to be by Professor Pietro Savos, and the talk is multi-channel time-resolved spectroscopy system. Pietro?
Yes, thank you. Let me just. Thank you. It's great to see all your faces. So, in contrary to what Robert just said, this system is going to be even bulkier and bigger. And the goal is actually to combine the time-resolved NIRS and high-density diffuse optical tomography and use it in clinical applications as well as functional NIRS applications. So in general, the multi in this case means we are using 32 photomultiplier tubes combined with 32 time-correlated single photon counting electronic. The modules are from Becker and Hickel, and we are also using 8 times 2 wavelengths laser diodes. So we have 16 in total of wavelengths 690 and 950. So this is the system is still in a development phase. So we managed to actually put all 32 TC-SPC electronic cards into a single rack. The whole system is going to be in a single 19-inch rack. So at the moment, all the TC-SPC electronics and PMTs are working. We are gathering the signals. On the right side, you can see the 4 racks filled with 8 PMTs each. And since we are using just 8 of these sets of 2 laser diodes, but they are quite powerful, each of them is around 50 milliwatts. So we are using these tricky fibers to actually be able to deliver the optical signals to actually 2 points on a head. So this is an example of the distribution of emitters and detectors on a head. And in total, we're going to have 16 emitting points and 32 detecting points. And if we assume the count rate on a level of 1.5 megahertz per lambda per wavelength, then at a refresh rate of 1 hertz, we're going to get around 180 kilophotons per distribution of time of flight. Like I said, this is a development phase. So we have few problems to solve it. The first one, this is the connection between the photomultiplier tubes and the fiber bundles. This is the designed connector. We still have to test it and manufacture that. Another one, this is a tricky one because we need some external, let's say, sync amplification and distribution electronics. We needed actually to connect every laser diode with all 32 TC-SPC electronics. Then we have to implement our algorithm on a Tesla graphic card with CUDA technology. We want to have the online reconstruction, and then we have to program the delay digital generators to achieve to control laser multiplexing. And finally, we have to implement a method to measure the instrumental response function. Okay, so why combination of time resolved and high density diffuse optical tomography? So in general, we're going to be using time resolved NIRS to increase the depth sensitivity. We're going to be using statistical moments of distribution of time of flight, and we're going to combine it with this high density distribution of emitters and fibers. And finally, we're going to, on top of that, we're going to be using the CUDA technology plus the NIFA software. And at this point, I have to acknowledge Stanisław Witkiewicz, he's going to be dealing with the 3D tomographic reconstruction of hemoglobin. Thank you all for your attention.
Thanks, Pietro. Thanks for taking up the time. So our next talk is going to be by Professor Alessandro Torricelli. And the title of the talk is Recent Advances in Time Domain of NIRS.
Yes, thank you. I'm trying to share my screen. Okay, can you see?
Yes.
Okay. So I will show you the recent advance in time domain NIRS that we are developing here in Milan. Actually, we are working on physical models in collaboration with Fabrizio Martelli, instrument development going from laboratory system to prototypes and medical device, and in parallel we do clinical application that right now are on hold due to the COVID-19 emergency. So in this talk, we only described some recent advance in hardware. And on the same tune as a previous talk, we like time domain NIRS and wearable. So a couple of years ago, we decided to implement what we call time domain NIRS in a box, so the NIRS box, and everything was done in-house with the pulsed laser, silicon photomultiplier for detection, and time to digital converters. Very recently, we have decided to improve the design and implementation of the NIRS box, achieving better performances for what concern accuracy in the estimate of optical properties and hemodynamic parameters, stability in counting and timing, and reproducibility over time. More important, the system is battery operated and wireless control, and also can perform online analysis. And I will show you some example of application. The first one is a test during cycling. So the probe was worn as a backpack, and the probe was put on the muscle, and the guy was alternating riding and resting. And the nice thing is that we also tested the presence of possible motion artifacts by placing a solid phantom between the probe and the muscle, and we got basically no artifacts. Then we tested the combination of two systems, one monitoring the arm and the other monitoring the forehead during a standard breath holding experiment. And as we can see here, the saturation on the arm nicely followed the saturation monitored by the pulse oximeter, the peripheral oxygenation, while in the head, in the bottom, we have no basically change in the saturation. more interestingly, we also wanted to test some motor task. So like finger tapping and walking. We placed the sensor on the C1 and C3 motor area. And then on one subject, we perform 5 trials of finger tapping here in the bottom row, in the top row. And then we did forward walking and backward walking, both with open eyes. And here we have the 5 repetition of each experiment, showing the nice activation in all the experiments. Then by using the capability of time domain needs, we were able to check the fact that the signal was coming from cortical region, so intracerebral. And in the bottom line, we see here that if we focus on early photons, we are basically sampling the extracerebral layer and we see no signal. While if we go to late gates, we have a nice signal from backward walking and forward walking, and no signal when the person is standing. Then we repeated the experiment on 3 subjects. So the first row is for the first subject. This is the folding average of 5 repetition, like shown on the left. And so we have the second subject in the middle row and the third subject in the third row. And the nice thing is that we had comparable results for what concerned the finger tapping and the forward walking and the backward walking between the subject. And the nice thing is that there seems to be a quite increased response for oxygenation in the backward walking, suggesting in higher involvement of cortical areas. We wanted to add some quantitative analysis on that, so we did some fitting with an adaptive hemodynamic response function, like published by Uga and colleagues in 2014. And here we got the results for the amplitude and the delay of the hemodynamic response function for oxy and deoxyhemoglobin, showing that for oxy we have an increased signal in effect when we have backward walking, but no main differences in the delay. For deoxy, on the contrary, we have a significant difference between walking and finger tapping in terms of the delay. So we believe that this is a nice tools that we can implement, can use when doing neuroimaging studies. And if you are interested in using it, you can also try to buy this, because right now we have just launched this startup company. And if you are interested, you can. That's done.
Okay, thanks, Alessandro. So I'm gonna pass this to my colleague, Adam.
Yes, let me introduce Maria Angela. Maria Angela, now it's your turn.
Mari, are you muted?
We don't hear you.
I was muted. I apologize. Share screen. I knew it. I had too many things. Okay. You can see me now and you can hear it. Okay. Let me start. Let me start with a super short overview of my lab at Martino Center and its amazing member. We build new NIRS devices. Current devices we're working on are time domain DCS, acousto-optic modulated interferometric DCS, multicolor DCS, a wearable cerebroximeter called FlexNear, and we build all our optical probes. We develop software interface for these devices and develop new data analysis algorithms. We perform initial experiments in phantoms, small animal, and healthy subjects, and quickly move to the clinic to test the new equipment in patients. Our focus working in a hospital is on clinical application. Current active projects include the study of intraventricular hemorrhage in premature infants, the validation of intracranial pressure measurements with DCS in stroke and traumatic brain injury, the monitoring during cardiac surgery and during carotid endarterectomy. We have several collaborators. Here I'm listing Felipe Espina, who helped us with the stats in several projects, and Stefan Karp, who helped us with everything. I need to disclose a conflict of interest. I have a startup company with DCS. The first project I want to tell you about is the development of a high-end time-domain DCS system operating at 1064 nanometer with many source and detector channels to allow for large head coverage and high resolution. This is a big engineering effort where we need to build most components from scratch. Nissan has been developing the optimal laser for these applications. We start with 1 nanosecond full width maximum seed laser and make it more narrow with an electro-optic modulator. We select the part of the seed laser with the highest coherence length, the one with higher beta, and we are able to achieve an almost transport limited beam and amplify it to 100 milliwatt with a second stage fiber amplifier. Meanwhile, our collaborator at Lincoln Lab are developing the indium phosphate photon counting gated detectors. They built the first ROIC, they hybridized it, and they are now testing it to decide the best macropixel configuration. We don't only develop super expensive devices. In the last few months, we've been working on a low-cost wearable wireless cerebral oximeter. Our prototype is based on a flexible PCB. It has 6 channels in 2 color, costs only $50, and acquires data at 100 Hz. Most important, this little device has outstanding performances. Here you can see the intensity at the 3 distances acquired on a subject. And if I zoom in at the larger separation, you can see the arterial pulsation and respiration very well. Our plan is to soon to make everything open source and deploy the FlexMir in community health and low resource setting applications. Finally, moving to clinical application, one important example is the monitoring of a extreme premature baby with diffuse Gaussian spectroscopy. In this study, we want to demonstrate the relationship between unstable cerebral blood flow and incidence of intraventricular hemorrhage. To allow for safe, long monitoring sessions, we have developed a super small and lighted probe that fit in these super small babies and detect probe detachments via a built-in capacitance and immediately shut down the lasers. The safety features also allow us to conduct remote monitoring, very important during COVID-19. Up here is an example of cerebral blood flow monitoring in a 23-week gestational age baby, the youngest we have ever measured. To interpret blood flow changes, we also acquire near-infrared spectroscopy oxygenation, pulse oximetry XPO2, and arterial blood pressure. In particular, as shown below in another example, John is finding a strong correlation between cerebral blood flow and arterial blood pressure around the time of an intraventricular hemorrhage, and lower correlation later on. These and other similar results suggest the loss of cerebral autoregulation as a possible precursor of intraventricular hemorrhage. Thank you for listening. Thank you, guys.
Thank you very much, Marie. We switch to David Bush of University of Texas Southwestern. David.
Hello, good morning, evening, what have you. So, a little bit of a shift in topic from the brain down to the spinal cord. And
David, we don't see your slides.
oh, you don't? One
Nope.
moment. Do you see my slides now?
Yeah.
All right. Thank you. All right. So we're shifting slightly down from the brain down to the spinal cord, and this is work that's I've been doing with Tom Floyd here at UT Southwestern. So there is a lot of ischemia in the spinal cord, And this may come from what you'd expect, trauma, or even surgeries to correct spinal cord deformities. But it also comes from a fairly common aortic aneurysm. When a stent is placed to cover the aneurysm, that stent may in fact cut off the little arteries that feed the spinal cord. So this works out to be roughly 300,000 people a year in the US. And the current monitors are based on the electrical transmission of the nerve fibers in the spinal cord. They're neither sensitive nor specific, and they've got about a 20-minute delay or up to a 20-minute delay between the inciting event and the actual drop-in signal. So what we've done over the years is develop an epidural spinal cord probe. Now you may have heard of epidural anesthetics. These are anesthetics which are placed into the epidural space of the spinal cord in between the bone and the dura, which lies over the spinal cord itself. This is placed using a TUI needle, which is in the upper right. And this device is routinely placed by anesthesiologists and others with a very low complication rate. We've developed a fiber optic probe which can fit through one of these standard needles. And the typical thing, we have a source, a couple of detectors, and we've spread out 3 sets of these sources over about 20. That allow this to be imaged in the operating suite with X-ray. These end up being tungsten or gold because we have these probes are only 1 millimeter wide. There's not a lot of space to work with. And when we measure blood flow, saturation, and hemoglobin over time, this is during a hypoxia experiment in a pig model, we see that as we expect, the blood flow increases, the saturation drops, and the hemoglobin increases due to blood vessel dilation. In a experiment designed to simulate the stent I just described, we've introduced a aortic balloon. These are used in emergency cases to prevent aneurysms, to prevent bleeding out due to massive injury to the lower body. And this balloon can be placed at multiple places in the aorta, inflated, and cutting off blood flow below the balloon. Here we start out with the balloon above all of our sensors. We've got 3 DCS sensors, and then we included a laser Doppler sensor as well. And as we pull the balloon down, you see that we can resolve where it is located. Now, this seems perhaps fairly obvious to people working in our field. However, it is a unique capacity in the spine surgery system. We've got a number of spine surgeons who are quite interested in this, because right now all the monitors they have tell them is that there is a problem somewhere in between the brain and the feet. And that's a lot of area to figure out where you've got a problem. So there's another project going in our lab in pediatric critical care, specifically on ECMO. And I've got some postdoc positions available. So if you're interested, please get in touch. And this is being done by these people here. And thanks also to Rickson, who did some of the initial work on this project.
Thank you very much, David. And we switch to the last talk by Peyman Mirtaheri from Oslo Metropolitan University. Peyman.
Thank you, Adam. Can you all hear me?
Yes.
Fantastic. First of all, thank you to the organizer, Mari, David, and Clara for a great idea. This was wonderful. Please let us continue this in the future. This is a great idea. So I'm coming from Oslo Metropolitan University, and we are a very tiny group working on FNIRS. And in fact, we started actually in 2017. The first FNIRS device that we got in a lab was in 2017. So we're just trying to develop what we have also in addition. And this project is part of what we have been done so far with some of our PhDs. So before I started it, most of the applications that we are using is lower extremities with amputation and how the brain is activated with regards to these amputees patients. One of the issues that is quite interesting is that we need to test these subjects out of the lab. And even if you're testing them in a lab, it has to be a space where they're walking in a lab. So basically, the ambient light issues is one of the issues. And if I may just repeatedly say this, with regards to reflection-based measurements, if there are, the goal is to measure the absorbance, you may have your light source and your detector towards that tissue. However, if there is any ambient light, you may have some sort of additional issues, in particular if you're having continuous wave measurements in your focus. So how is the approach to just avoid some of these issues is that maybe just place a sort of container around that tissue, which is sometimes a sort of a black hat. In some cases, it is a shower cap. Most people call it also as overcap. And the thing is that it may solve some of the issues, but sometimes it has some sort of additional problem that is introduced by these overcaps. One of them is that it can actually increases the temperature inside that cap itself. And that may produce some sweating. And remember that sweating is not always a positive thing to get much better contact in that sense. We actually did some measurements back in time with some of these overcaps that we had in our disposal. And the reason that most of the people are using the black color is perhaps because they want to sort of filter out all the visual range of the light, which is actually functioning. However, if your measurements is in near infrared range, then that kind of a textile is not 100% blocking that light. And if you have any kind of a tension in addition to that textile, it is actually changing its transmission. So in our case, we could actually detect something like almost twice of transmission if you just stretch this type of textile. Unfortunately, we didn't have on that time access to other materials. But if anyone is interested to do that, we have the equipment. Please contact me. We can just do this and publish this stuff further together. So we have, in this work, tried to suggest a strategy, which we call as a SHADE strategy. And SHADE stands for Absorption Spectroscopy Enhancement with Ambient Light Estimation and Narrowband Detection. So the strategy is based on 4 points. The first part is frequency division methods, wavelength. So we're using multiplexing, demultiplexing in our hardware. Then we use inverse notch filtering in order to get a robust signal detection. Then we use the third point, which is the simultaneous ambient light intensity measurements while the LEDs or the light sources are off. So when the system is not on states, we are detecting the ambient light levels. And based on that, we can actually make a model that our DSP is generating that model, and we correct for any dynamic ranges. Of course, this is dependent on how much of ambient light we're talking about. If it is a sunbathing under direct sun, of course, this equipment is not gonna function. But we have been trying this stuff with different type of adjustable lamps, some exposure of sun lights, and then it is promising, but it's not 100% clear. The results are not 100% with regards to that yet. So the idea is, again, we are making this FNIRS device with sort of module-based with 3 wavelengths. At the same time, we're detecting the light when these light sources are off. And based on that, we're just using a sort of post-processing ambient noise removal algorithm. And basically, what is the positive thing with this idea is that we may be able to just do this post-processing based on sampling. So you're just one sampling time behind the correction, but it's always getting in the level of correction almost like simultaneously.
You pass your 5 minutes.
I'm finished. So this is just an idea of how this is functioning, and then this is some of the results that we have. Last part is, of course, our PhDs, Habib Shirket and Marco Pinto, who have been contributing to this. You may find the paper on Optic published in 2020. Thank you.
Thank you very much, Payman. We switch to questions and answers session. I just looked through this website. There are plenty of comments and questions, very interesting discussions, also related to very detailed problems. One question was repeated several times. It's about hairs, especially in Rob's system. Rob, could you tell us more about how you solve the hairs problem?
Sure. I was just answering a few questions over text. So, well, in the infant, it's easy, or easier at least. So, like most of the infant studies with existing devices, we used basically a flat probe, and you effectively don't have time in the infant population to go around on every probe and move them. So you just have to have a system that's sensitive enough to not worry about that. We've only done the one study with a population of 20 so far, so I can't. I don't know if we got lucky, but in our population, we didn't lose a single baby because of data quality. We lost 3 babies out of 20 because I screwed up and deleted the data, but we didn't lose any babies because of data quality. So in terms of hair in the infant, it's straightforward. In the adult, like all FNIS systems, it's more challenging. And one of the trade-offs with the high density devices is obviously it's much harder to go underneath every single optode and move hair. You just don't have the time. So you have to kind of develop a mechanical way of solving that problem. So it's probably hard to see this from my slides, but there's a part at the front side of the system that is removable that you can interchange for like a flat one for infants or a comb-like one for adults. So we're taking that approach. You can toggle the whole system, and you can usually get over hair. And I mean, I think it helps that the systems are actually pretty sensitive. The gain's pretty high. So generally speaking, it's a challenge, but it's a solvable challenge.
Okay, thank you very much. There are plenty of more detailed questions to Rob, but he answered many of them already online. The question which I like to David Bush is how to switch with this concept to human studies. Do you have any idea? Is it possible, feasible to do it in humans?
Yeah, thank you. Yes, it's quite feasible.
So what are the obstacles
in the epidural space? And there's a history of placing spinal cord stimulators using electrical signals to reduce pain, and there's also some work for paralysis. This has already been taken to the FDA, and we're moving forward with that. We're a little bit delayed with the current circumstances, but we hope to be doing first in humans in 18 months to 2 years.
Okay, thank you very much. There is interesting question to David Boas about the data sharing vision. There's a long answer, but maybe you can share some more.
Sure. I mean, I'll just repeat for everyone kind of what I wrote, and happy to discuss more. Not really vision is something we've been discussing, at FNIRS conferences the past many years, where everyone wants to share their FNIRS data sets. More and more people are entering the field. They're looking for data sets to practice analyzing on, or maybe test new algorithms on. So, really want to encourage everyone to share their data. I believe many people already are doing that on many different repositories. Now that SNRF is available and many people in the community have worked to develop that, I think that will facilitate the sharing of data. What we just did on openfnears.org, this website that we created to facilitate the sharing of software and hardware, was we just created a database there, a table, to act as a metadatabase where since actually there's literally dozens of repositories out there for sharing data, we don't really know where to find the FNIRS data. And so this openfnears.org/data could serve as a repository, a metadatabase of all the openly available data sets. So we've put 6 out there on that database. Just encourage many others to do the same and let us know where it is, and we'll put it on the database.
Thank you very much. I like very much the question from Joe. Actually, where are the 2 big challenges which you recognize in your systems? This is actually to all of presenters. Where are the big challenges, and which of them which of the problems which we had on the list in last years were really solved in these systems? Could you comment on that?
I can
Alessandro?
Go.
Yes, can you hear me? So, well, the idea was to squeeze a time domain system in a box, and up to now we made it with 1 channel, 2 wavelengths. Actually, this is just the first step, so there is basically no big problem in implementing in a multi-channel, not the way that Piotr has shown. I mean, we want to keep the dimension smaller, but of course there can be some problem with the, I mean, on our side, the problem is funding, basically. So this is also the reason why we have funded the company, just to gather fund and to exploit this concept in a more industrial way, because limiting to the university, this is not possible.
I'd like to say, I think all the hardware challenges are being solved. Everyone's made tremendous progress here. I think really going forward, it's doing good science with it, out there in the world. And how do you analyze that data? It seems to me that's going to be a big challenge and a lot of fun working on.
Rob, could you comment on that?
Yeah, I mean, I think I agree with David. I think if you look where we were as a field just 5 years ago, I think on every front really the hardware's making huge gains, and I think there was a phase maybe 10 years ago where it was really the software that needed improvement. And with packages like Homer, I think they filled that gap, and as some of these technologies were demonstrated in the lab, there was then this kind of hardware gap, and now we've filled that gap, and now we're back to software again, I think, to some extent at least. So, I mean, from my point of view, scaling up these devices to be whole head has always been something I've aimed to do, and that's been a goal of ours for a long time, because I think as a community, it's the only way we're going to ever standardize these tools. We can't keep having different arrays for every experiment and expect to have consistent data processing in place. So that's really the goal that we're working towards. Couple that with all the advances in miniaturization of time domain, and it starts to look really exciting for the next few years, I think.
So for me, DCS, the hardware, there is still a lot to do. There are many work coming out, going interferometric, going with big camera. The way we detect speckle is still very open. So while for NIRS, the hardware is there, for DCS, there is a lot of hardware that we still need to come, and there will be big improvements, I think, in the next few years with DCS hardware to improve SNR.
One more question to Alessandro. How did you reach the high temporal resolution? How it was possible to get pulsations in the time resolved signals?
Actually, we haven't tested this, but I think it is feasible. I mean, there is only a trade-off between signal to noise. I mean, if you reduce the acquisition time down to 10 milliseconds, you can easily see the heartbeat if you have enough photons. So in the existing system, if I'm not wrong, we can go down to, say, for sure, 100 milliseconds measurements. In laboratory system, we can improve up to 250 hertz, if I remember well. So, but system with the components similar to the one that your group has shown, Adam.
Thank you very much. And last question to Rob. Do your channels have fixed gains?
So the system, that's a Galab's question really. So the system allows you to automatically adjust source powers on the fly. It's a frequency multiplex system. I'm not sure I can say much more than that. You probably have to check the website.
So thank you. I think we finished. Thank you very much for great presentations and very good timing of presentations. We had also very nice discussion. Thank you very much, and thank once more Maria Angela for arranging this. I think this is a great idea and very interesting session we had. Thank you very much.
So thank you a lot, Adam. We're about to start the next session. We are in perfect timing. I want to remind everybody that you can continue to ask